Hello, everyone. Today we're going to uncover a fascinating concept in chemistry called hybridization. Imagine that in molecules like methane, CH4, ammonia, NH3, and water, H2O, atoms arrange their bonding electrons in unique ways to produce the shapes we observe. But how exactly do atoms decide on these shapes? Well, Linus Pauling introduced the brilliant idea of hybridization to explain this. Hybridization is the process where atomic orbitals of an atom, like the s and p orbitals, mix or hybridize to form new orbitals called hybrid orbitals. These newly formed orbitals are all of equal energy and shape, unlike the original pure orbitals. It's like mixing different paint colors to create a new, uniform shade. For example, when one 2s orbital and three 2p orbitals of carbon combine, they form four new sp3 hybrid orbitals, all identical in energy and shape. These hybrid orbitals are what carbon uses to form its bonds in methane, giving the molecule its characteristic geometry. Think of hybridization as an organization method in the atomic world, where orbitals get reshuffled to create the strongest possible bonds and stable structures. Throughout our lecture, we'll explore this concept deeply, connect it with molecular shapes, and understand why it's so important in chemistry. Ready to dive in? Let's begin. Let's explore the key features of hybridization. Step 1. When orbitals hybridize, the total number of hybrid orbitals formed is equal to the number of atomic orbitals involved in the mixing. So if we mix one s orbital and three p orbitals, we end up with four hybrid orbitals. Step 2. These hybrid orbitals are not just random. They are exactly equivalent in both energy and shape. This equivalence is essential because it means the atom shares its electrons evenly in chemical bonds. Step 3. Hybrid orbitals are better at forming stable bonds than pure atomic orbitals. Since they are directed in space, hybrid orbitals overlap more effectively with orbitals from other atoms, creating stronger bonds. Step 4. The hybrid orbitals orient themselves in specific directions to minimize repulsion between electron pairs. Electron repulsion is like trying to keep friends comfy on a couch by spreading them apart for maximum space and least disturbance. Finally, step 5. The type of hybridization, whether sp, sp2, or sp3, directly determines the geometry or shape of the molecule, explaining why some molecules are linear, trigonal planar, or tetrahedral. Isn't it wonderful how nature arranges tiny electron clouds in an orderly fashion? Imagine if atoms didn't do this. Molecules would look very different. Before we get deeper into hybridization types, let's understand the important conditions governing this process. Firstly, hybridization involves only the orbitals present in the valence shell, which is the outermost electron shell of an atom responsible for bonding. Secondly, the orbitals that hybridize should have almost equal energy levels. Imagine trying to blend two musical notes. If their pitches are close, they harmonize beautifully. Similarly, orbitals need similar energies to mix well. Thirdly, it's not essential for electrons to be promoted or excited prior to hybridization. That means an atom can hybridize without first rearranging its electrons to higher energy orbitals. Finally, not only half-filled orbitals, but sometimes even fully filled valence orbitals take part in the hybridization process. This flexibility makes hybridization adaptable to different bonding scenarios. Knowing these conditions helps us predict when and how atoms will hybridize to form molecules. Cool, isn't it? Just like a chef mixes ingredients for the perfect dish, atoms mix orbitals following these rules. Now let's jump into the first type of hybridization, sp hybridization. Step 1. sp hybridization occurs when one s orbital mixes with one p orbital from the same atom's valence shell. This creates two new hybrid orbitals that are exactly equivalent. both having 50% S character and 50% P character. Think of it as mixing equal parts of two colors to get a balanced new shade. Step 2. These sp hybrid orbitals align linearly along the z-axis, pointing exactly opposite each other, creating a 180-degree bond angle. This explains why molecules with sp hybridization adopt a linear shape. Imagine two friends standing back to back, perfectly aligned. This model is sometimes called diagonal hybridization because the orbitals hybridize diagonally in terms of energy and shape. Understanding sp hybridization helps us grasp how some simple molecules maintain their shapes and bond angles. Ready to learn about a real example? Let's move to that next. Let's bring sp hybridization to life with beryllium chloride, BeCl2. In its ground state, beryllium has an electronic configuration of 1s squared, 2s squared, meaning its 2s orbital is full. However, when forming BeCl2, one electron from the 2s orbital is promoted to the vacant 2p orbital, preparing the atom for bonding. Now the 2s and 1,2p orbital combine to form two equivalent sp hybrid orbitals. Refer to figure displayed on your screen. You can see the spherical s orbital on the left, the dumbbell-shaped p orbital in the middle, and on the right, the two linearly arranged sp hybrid orbitals at 180 degrees. These sp hybrid orbitals point in exactly opposite directions along the z-axis, minimizing electron repulsion and lending the molecule a linear geometry. Each of these sp hybrid orbitals overlaps head-on with the 2p orbital of a chlorine atom, forming two strong sigma bonds. This overlap is what holds the beryllium chloride molecule together. Imagine two people stretching their arms directly away from each other, holding hands with others. That's how these orbitals connect, forming a stable linear molecule. Now think for a moment. Why is the bond angle exactly 180 degrees? What would happen if it was less? Pause and reflect for 15 seconds before we head to the next hybridization type. Moving forward, let's explore sp² hybridization, pronounced sp2. Step 1. sp2 hybridization occurs when one s orbital mixes with two p orbitals, creating three equivalent hybrid orbitals. Each sp² hybrid orbital consists of about 33% s character and 67% p character, meaning the s contribution is less than in sp hybrid orbitals. Step 2. These three orbitals arrange themselves with 120-degree angles in a single plane, forming a trigonal planar geometry. Imagine a perfectly flat tripod with each leg spread 120 degrees apart. This arrangement reduces electron pair repulsion because the orbitals are as far from each other as possible on one plane. Step 3. Molecules with sp2 hybridization, like boron trichloride, BeCl3, assume this flat trigonal shape. This geometry is common in molecules with double bonds, as we will see soon, and explains their planar structures. Before the next slide, take a moment and picture how changing the number of p orbitals in hybridization changes the molecular shape. Fascinating, isn't it? Let's take boron trichloride, BeCl3, as a perfect example of sp² hybridization. The electronic configuration of boron is 1s², 2s², 2p1, meaning it has one unpaired electron in the 2p orbital. When forming BeCl3, one electron from 2s is promoted to the 2p orbital, resulting in three unpaired electrons. Now one 2s and two 2p orbitals hybridize to form three sp2 hybrid orbitals. Look at figure displayed now. You can see on the left the s orbital mixing with two p orbitals, resulting in three equivalent lobes arranged 120 degrees apart in a flat plane. On the right, the boron atom uses its three sp2 hybrid orbitals to overlap with two p orbitals of three chlorine atoms. This overlap produces three strong sigma bonds, holding the BCl3 molecule in trigonal planar shape. The bond angles are exactly 120 degrees, like a perfectly shaped equilateral triangle. This arrangement results from the effort to minimize repulsions among orbitals. Try imagining a three-pointed star lying flat on the table with equal spacing between points. That's how the molecule looks. To deepen your understanding, can you think of other molecules with similar trigonal planar geometry? Here's your moment for thinking. Up next is the most well-known hybridization, sp-cubed hybridization, or sp-cubed. Step 1. This involves one s orbital mixing with three p orbitals to form four equivalent sp3 hybrid orbitals. That means four new orbitals identical in energy and shape. Step 2. Each sp3 hybrid orbital is made up of 25% s character and 75% p character, so the p contribution is dominant. Step 3. These four orbitals spread out symmetrically, pointing towards the corners of a tetrahedron at bond angles of 109.5 degrees. Imagine four friends standing at the corners of a pyramid-shaped tent, all equally spaced. This model beautifully explains molecular shapes like methane, CH4, where the carbon atom forms four equivalent bonds with hydrogen atoms, producing a stable tetrahedral shape. Understanding this arrangement gives us deep insight into why molecules have their characteristic 3D shapes and bond angles. It's like nature's way of creating molecular architecture. Ready to see this in action? Let's move on to the example of methane. Let's dive into methane molecule, CH4, and see sp3 hybridization in action. Carbon's valence shell has one 2s orbital and three 2p orbitals, one along each axis x, y, z. These four orbitals hybridize, mixing their energies to form four new equivalent sp-cubed hybrid orbitals, each pointing towards a separate corner of a tetrahedron. This arrangement positions them 109.5 degrees apart, minimizing repulsions. Refer to figure on your screen. On the left, you see the combination of s and 3p orbitals. On the right is methane's tetrahedral shape, where carbon, center, forms four equivalent sigma bonds by overlapping each sp3 orbital with the one s orbital of a hydrogen atom. This overlap results in strong CH bonds, structurally holding the methane molecule in its characteristic shape. Think of carbon as the host of a party, offering four arms equally spaced to hold hands with four guests, the hydrogens. Pause for a moment and imagine what would happen if those arms weren't equally spaced. The party wouldn't be so stable or comfortable. Thinking time. Why do you think the bond angle is 109.5 degrees instead of 90 degrees or 180 degrees? Reflect for 15 seconds. Let's discuss ammonia, NH subscript 3. A classic example of sp3 hybridization with a lone pair. Nitrogen in its valence shell has 2s squared, 2px1, 2py1, and 2pz1. These four orbitals hybridize to form four sp-cubed hybrid orbitals. In NH, three of these sp3 orbitals overlap, with the 1s orbitals of hydrogen atoms forming three NH sigma bonds, and the fourth contains a lone pair of electrons belonging solely to nitrogen. Look at figure displayed for you. Nitrogen is at the center with three hydrogens bonded around it. The blue lobes represent bonding orbitals, and the lone pair, LP, is labeled clearly pushing the bonded hydrogens down. Because lone pairs repel more strongly than bonding pairs, the bond angles decrease from the ideal tetrahedral 109.5 degrees to approximately 107 degrees, giving ammonia a trigonal pyramidal shape. Imagine the lone pair as a stubborn guest at a party taking up more space and pushing the other guests closer together. Pause for 15 seconds and think, how does the lone pair affect the shape and bond angle? This concept will help you understand more complex molecules ahead. Water, H2O, is a molecule that beautifully demonstrates sp3 hybridization and the effect of lone pairs on molecular shape. Oxygen has 4 valence orbitals, 1 2s and 3 2p. These hybridize to form 4 equivalent sp3 hybrid orbitals. 2 of these contain lone pairs of electrons that belong solely to oxygen, and 2 form bonds with hydrogen atoms. Take a look at figure with me. Oxygen is in the center with 2 hydrogens bonded, and 2 lone pairs labeled LP, represented as blue lobes. The lone pairs push the hydrogen bonding lobes closer, bending the molecule. Because lone pairs repel more than bonding pairs, the ideal tetrahedral bond angle of 109.5 degrees shrinks to approximately 104.5 degrees, giving water its famous bent or V-shaped geometry. Water's shape explains many of its unique properties, including its polarity and hydrogen bonding capabilities, vital for life. Pause and think for 15 seconds. How do lone pairs influence water's shape compared to ammonia or methane? You'll discover the beauty of molecular architecture here. Let's now look at the ethane molecule, C2H6. In this molecule, both carbon atoms adopt the sp3 hybridization state. Step 1. Each carbon forms 4 sp3 hybrid orbitals. One of these sp3 orbitals from each carbon overlaps directly to form a carbon-carbon sigma bond, a strong single bond connecting the 2 atoms. Step 2. The remaining 3 sp3 orbitals on each carbon overlap with the 1 s orbitals of hydrogen atoms to form carbon-hydrogen sigma bonds. This arrangement results in each carbon having a tetrahedral geometry, similar to methane, with bond lengths roughly 154 picometers for CC and 109 picometers for CH bonds. Imagine 2 tetrahedral tents pitched next to each other sharing a side. That's how the carbon atoms bond in ethane. Pause a moment and think about how the overlap of orbitals contributes to the molecule's stability and shape. Why is orbital overlap directional and important for bond strength? These ideas are fundamental to understanding organic molecules and their behavior. Now let's discuss ethene, C2H4. A molecule known for its double bond between carbons, demonstrating sp2 hybridization. Each carbon undergoes sp2 hybridization, mixing 1s and 2p orbitals to form 3 equivalent orbitals. 1 sp squared orbital of each carbon overlaps directly to form a carbon-carbon sigma bond. The other 2 sp2 orbitals on each carbon overlap with 1 s orbitals of hydrogen atoms to form carbon-hydrogen sigma bonds. The remaining unhybridized p orbital on each carbon lies perpendicular to the plane and overlaps sideways with the p orbital of the other carbon to form a pi or pi bond. Looking at figure 4.15, you can see that the double bond between carbon atoms consists of 1 sigma bond, and 1 pi bond. This arrangement limits rotation around the bond axis, giving ethene rigidity. The carbon-carbon bond length is shorter at 134 picometers due to the double bond. Also, the bond angles slightly deviate from perfect trigonal planar with HCH around 117.6 degrees and HCC approximately 121 degrees. Pause and reflect. How does the presence of the pi bond influence molecular shape and reactivity compared to a single bond? Finally, let's study ethane, also known as acetylene, with the formula C2H2, showcasing sp hybridization and triple bonding. Each carbon atom in ethane hybridizes by mixing 1s and 1p orbital to form 2 sp hybrid orbitals, leaving 2p orbitals unhybridized. 1 sp orbital from each carbon overlaps end to end, forming the strong carbon-carbon sigma bond, while the other sp orbital overlaps with hydrogen's 1s orbital to form carbon-hydrogen sigma bonds. The 2 unhybridized p orbitals on each carbon overlap side by side in perpendicular planes, forming 2 pi bonds, resulting in a carbon-carbon triple bond. Referring to figure, you can observe the sigma bond along the internuclear axis and the two pi bonds above and below this axis, providing the triple bond its rigidity and strength. This triple bond shortens the carbon-carbon bond length and restricts rotation, significantly affecting the molecule's chemistry. Think for a moment. How does overlapping in two different planes create a stronger bond? Pause for 15 seconds before we conclude. As we conclude our lesson, let's summarize the key points about hybridization types and their molecular geometries. First, sp hybridization involves mixing one s and one p orbital to form two hybrid orbitals. Molecules like beryllium chloride and the sigma bonds in ethane have linear geometry with bond angles of 180 degrees. Next, sp2 hybridization mixes one s and two p orbitals, forming three hybrid orbitals with trigonal planar geometry. Examples include boron trichloride and ethene, featuring bond angles of 120 degrees. Then, sp3 hybridization involves one s and three p orbitals, producing four hybrid orbitals in a tetrahedral arrangement with bond angles of 109.5 degrees. Methane, ammonia, and water molecules exhibit this type. Do remember the presence of lone pairs modifies shapes and bond angles, as seen in ammonia and water, due to stronger lone pair repulsions. Understanding hybridization gives us a powerful tool to predict molecular shapes, bonding types, and even reactivity patterns in chemistry. I encourage you to keep exploring these concepts, visualize the orbitals, and appreciate the elegance of molecular architecture. You are doing great.